Hi everyone and welcome to the internet. So what we're going to be doing in today's lesson is having a look at stretching materials and storing energy. So hopefully by the end of this you can explain the difference between linear and non-linear relationships. Start us off then, what we've got are 4 key terms that we looked at on Monday's lesson. So what I want you to do is in your books write me a definition for those 4 terms. Elastic, plastic, Hooke's law and elastic limit. So I'm just going to give you a couple of minutes to have a go at writing those down. Off you go. So let's see how we've done then. Mark these as you go. Obviously give yourself a tick if you got it right, and if you didn't get it right then make sure you do have the correct definition written down. So elastic is a material that returns to its original shape when we remove the force. Plastic is a material that will not return to that original shape when the force is removed. Hooke's law is where when we double the force on a spring we will double the extension until the limit of proportionality. I think you can give yourself 2 ticks for that one. One for doubling the force on a spring doubles extension, and the other for until the limit of proportionality. And then the last one, the elastic limit, is the point at which if the force is exceeded the material will no longer return to its original length. So give yourself a mark out of 5 and then give me an answer in the chat window as to how we did. Give me a number from 1 to 5. So what we're going to start off with looking at then is a formula here. So the energy transferred in stretching, and because we're talking about energy, the units will be joules, capital J, is 0.5 times the spring constant in newtons per meter times the extension in meters, but that extension is squared. Now, what we need to be careful of with this formula is how we use it. There is a bit of good news before we get into that, which is they give that to you on the physics formula sheet. Finally, we have got a formula they are going to give you in the exam, guaranteed. So you don't have to memorize this, we just need to know how to use it. In terms of how to use it, we've got to be really careful to remember that it's only the extension that is squared, not the whole thing. Now, what we could also say we're calculating here is the work done, because energy transferred is the work done. Now, there's a question at the bottom I want you to have a little go at answering for me. Why can't we use work is force times distance when we are calculating the work done in stretching? So have a little think, jot down your answer in your book. I'll just give you about 30 seconds just to write down what you think. So the reason that we can't use that is because the force is not a constant value. Okay, the next thing we're going to have a go at doing then is seeing how to use that formula in a calculation question. So what I've given you on the screen here is the same formula as before, but then I've given you an example question. So I'd suggest you jot this down in your book so that you can see a worked example. A spring is 4 centimeters long and has a spring constant of 500 newtons per meter. Calculate the energy transferred when it's stretched to a length of 7.5 centimeters. So I'll just give you a few more seconds to get the question written down before we go through how to answer this together. Now, the first thing we do, as always with a calculation question, is as we're reading it, we're going to underline, highlight or circle the key information so we don't have to keep rereading the whole thing over and over again. So you can see here I've highlighted the key information in red. We've got a 4 centimeter long spring, it's got a spring constant of 500 newtons per meter, we're calculating energy transferred, and it's being stretched to 7.5 centimeters. So those are the key bits that we've highlighted in red first of all. So do the same in yours, either underline, highlight or circle those key bits of information just so it draws your eye to it. So the next thing we need to do then is to calculate the extension in meters. Now in our question it tells us the spring is starting off at 4 centimeters and it's being stretched to 7.5 centimeters. So to work out the extension we do our final length 7.5 minus the initial which is 4. That gives us an extension of 3.5 centimeters. But that's not where this bit ends because remember our extension is in meters. So what we need to do is convert those centimeters into meters. And hopefully we remember that in order to do that we divide by 100 because there are 100 centimeters in 1 meter. So 3.5 divided by 100 gives us 0.035 meters. So all that's left for us to do now is turn to the physics formula sheet, find our energy transferred formula, write that in first of all as it is. So energy transferred is 0.5 times the spring constant times the extension squared, and then we substitute in our values. So it's still 0.5 obviously, times our spring constant which is 500 from the question, and then we times that by the extension in meters, which we literally just worked out as 0.035, remembering that is going to be squared. Now, when you actually come to type this into your calculator, you've got a couple of options on how you can do this to get it right. You can start by doing the 0.035, square that, and then you can do the times 500 times 0.5, or you could use brackets. It's up to you, whichever one you are more comfortable with, then use that method. But just go careful not to just type in all of your actual calculation and then end up squaring the whole thing because obviously you won't get the right answer. So once we've typed that into our calculator we should come out with a value of 0.30625 joules. So make sure you've got that example written down and understand those key steps. If there's anything you're not sure of then obviously ask in the chat window so that we can run through it. Okay, so your turn now. Here are 3 questions. So you're using that same formula that we've just looked at, go through those same stages, and of course you can use a calculator. So have a go at answering those 3 questions for me. I'm just going to give you a few minutes to have a go at that. If you're stuck on anything, then ask in the chat window. Off you go. If you still need a little bit more time to finish those off, then pause the video now. Okay, let's just double check to make sure we've got those right. So our first one should be 0.75625, the second one is 0.49, and the last one 0.18. Give yourself a tick for each of those you got right, and let me know how you did in the chat window. Okay, what I want you to think about now then is what we'd actually need to consider if we were about to hook someone up to a bungee and then let them jump off a really high bridge. What would we actually need to consider before actually letting them jump? Hopefully we've come up with some of these key ideas. So we need to think about obviously the weight, and we then also need to think about the spring constant of that bungee cord. Because if we pick either the wrong bungee cord for someone's weight, or we don't record their weight correctly, then what's going to happen as they jump off that particular bridge, building, whatever it may be, is it could overstretch and lead to a rather unpleasant mess on the ground. Now, we also don't want it to be far too strong and therefore fling them up way into the air, creating rather unpleasant forces on the body. So we do need to consider the weight that will be exerted by that person and also the actual spring constant of the cord itself to make sure they are correct. Now, when we're thinking about a bungee cord, it's basically a slightly more enhanced but giant elastic band. Now, what we actually have for things like elastic bands is something called a non-linear relationship. And you may have noticed this, that when we actually pull on an elastic band, then initially it's a little bit tricky to get to actually stretch, but then you get past a certain point and it gets much easier to stretch it. So we've got this non-linear relationship. And I can show you the graph on the screen there. So you can see that the extension and the force don't increase by the same amount each time. So there's not that same relationship we saw with the spring. So what we see here is something that's different. It's a non-linear relationship. So question for you to have a go at jotting down in your books. Why can't you use an elastic band in a Newton meter? And I'd also suggest at this point that you actually do a little sketch of the graph there and jot down the fact that that is a non-linear relationship. So I'll give you a couple of minutes just to get the graph done and have a go at answering that question in your books. So hopefully we did point out the fact that if it's a non-linear relationship and we wanted to use our Newton meter then to actually work out the force exerted by a particular object, it just wouldn't work because it needs to have that linear relationship to actually convert into a force for us. Now, I want to give you another scenario to consider here. If you think about when you're blowing up a balloon, what I want you to do in your book is just jot down what you notice about the force you'd need to exert as you blow it up. So just jot down a couple of points in your book. What do you notice about the force you need to blow up a balloon as you actually inflate it? So what we've got here then are two other relationships where we can see the graph between the extension and the force. So what I want you to do first of all is just take a couple of minutes just to describe, so describe is to say what you see, so describe the shape of the graph for copper and the graph for glass. So I'll just give you 2 minutes to get that done. If you need any more time, just pause the video now. Hopefully what we talked about there then, for glass, first of all, the graph on the right, then we can see there's actually not much extension at all. So the glass will have the tiniest bit of extension when we apply a force, but then it will just break. So we don't really get that curve at the end like we saw with the spring because it's not having that same relationship. It's a very steep graph there. Whereas with the copper, if you look, that first part of the graph on the left, that is a straight line. So we do have that linear relationship to start with, but then you can see we get that curve coming around again. And then what we're going to find is that it will again snap. So we've got those two different graphs there just for different materials, but do remember that anytime they give you a question that says describe the graph, then all we're doing in a describe is we say what we see. So we're just describing the shape. We don't actually have to explain what's happening. So the last thing we actually need to do is we need to tie all of these ideas about the deformation of materials to energy. Now, what we actually find is that when materials deform, then they're storing energy within themselves. And what we can then do as a scientist is we can actually use that principle to design materials that are then able to transfer that stored energy they've got within their structure back when they regain their shape. And we'll design different materials that are deliberately going to remain permanently deformed after an impact. Now, obviously one of these materials that we'd want to remain permanently deformed would be something like the crash barriers you see on motorways. So those metal barriers that we've got running between the two sides of the motorway, the whole idea behind that is that in case of a collision, then it will obviously change shape with the force of the car hitting it, but it then won't return to its original shape. So what I want you to do is, in your books, just write down why you would not want the crash barrier to regain its original shape once an impact has occurred. So I'm just going to give you about a minute to do that. So hopefully what we've actually got written in our answer there is that the reason that we don't want our crash barrier to then regain its original shape is that if you imagine that a car has collided into that crash barrier, then the last thing we actually want to happen for the poor participants inside that car is for the crash barrier to then go back to its original shape, thereby just shoving the car away from the crash barrier, potentially causing further injury. So those are the kind of materials we want to stay deformed, because that process of deformation has actually given those people, hopefully anyway, fewer injuries, because it's given them longer to actually come to a stop, and that's better. And we'll learn more about that in one of our later physics topics. But key thing here is we don't want it to return to its original shape, because otherwise it's going to fling the car back into traffic and potentially cause more injuries. Okay then folks, final thing for today is of course our plenary task. So those of you with targets up to a grade 5, the 2 on the left, and those of you with targets over a grade 5, it's the 2 questions on the right. Again, I'll leave these up here for a couple of minutes to give you a chance to answer these in your books. If you still need more time, then hit pause on the video now. As usual, you can find the answers to those plenary tasks on my website. The link is on the screen for you now. And don't forget to join us next time for our next lesson. See you then.